Welcome to the next lesson, which covers the history of parallelism support in Java. In this lesson, you'll learn the history of Java parallelism from roughly 2010 to 2022. You'll also get a chance to understand the evolution of Java from its initial support on concurrency and concurrent programming to its more recent support for parallelism and parallel programming. We'll start a discussion with Java's foundational parallelism support, which came when the Java fork join pool and fork join framework were introduced in Java 7, which was released in roughly 2010. The focus of the fork join framework is on fine-grained, object-oriented data parallelism. In this model, the same task is run on different elements of data by applying the split, apply, combine model, which we talked about earlier when we discussed the fork join framework in detail, and also when we discussed the Java parallel streams framework. You can find an example in my GitHub repository that uses the common fork join pool to search input strings to locate phrases that match famous quotes by William Shakespeare. And this example shows how you can use fork join task to split the search space up in order to be able to cover that analysis in an embarrassingly parallel way. The fork join framework that was the initial support for parallelism in Java is very powerful and very scalable because it takes good advantage of multi-core processors. However, it's also tedious and error-prone to program directly. As we talked about earlier, there are issues with respect to white box frameworks. We have to override methods and fill in certain methods, and this can get a little tedious and complicated to program if you're not very careful. Therefore, starting with Java 8, more advanced parallelism support was introduced into Java. And this came by means of the Java Parallel Streams framework and the Java Completable Futures framework. The initial focus in the advanced parallelism support in Java was on fine-grained functional programming frameworks for data parallelism, namely parallel streams, as well as asynchrony, namely with completable futures. Here's a simple example that you can find in my GitHub repository that illustrates how you can use the support in Java for Java parallel streams to synchronously download images that aren't already cached from a list of URLs and then process and store those images in parallel. So this is a nice example because it shows how you can basically chain together the various aggregate operations in Java streams using a fluent interface model and then make it a parallel stream so that the computations are automatically mapped to the underlying threads in the common fork join pool, which itself automatically maps things to the underlying processor cores. There's also, of course, support for asynchrony with completable futures. If you take a look at this example, which you can also find in my GitHub repository, this combines Java sequential streams and Java completable futures to asynchronously download images that aren't already cached from a list of URLs, and then process and store those images in parallel using asynchronous mechanisms. And this example is particularly cool because it demonstrates how easy it is to integrate Java sequential streams and completable futures, where the streams framework provides the overall flow of control and the completable futures framework provides very highly optimized asynchronous processing. Later versions of Java, in particular Java 9 and beyond, focused on pub/sub reactive streams. So these were introduced with Java 9 with the Flow API, and then there are also a whole variety of different frameworks that implement the reactive streams APIs, including RxJava and Project Reactor. So they provide a more seamless integration of pub/sub and asynchronous processing and streams together. This is another example which you can take a look at in my GitHub repository, where it applies the Project Reactor framework and the reactive streams model to asynchronously download images that aren't already cached from a list of URLs and then process and store those images in parallel. And what's interesting about this particular example is it demonstrates something known as a parallel flux, which is a very interesting and powerful parallel programming framework that, again, combines these pub/sub and asynchrony and streaming models in one nice integrated package. Java's advanced parallelism frameworks are designed to strike an effective balance between productivity on one hand, making things easier for developers, and performance on the other, making things take good advantage of the underlying hardware and software resources. The one downside, of course, is that these frameworks can be a little bit overly prescriptive. If things fit within the models that they provide, in particular, if they fit with things like a divide and conquer model, then parallel streams works great. If they work with an asynchronous model, then completable futures works great. but sometimes you need a little bit more flexibility. Let's also talk about the evolution of Java from concurrency, which was its initial focus, to its more recent parallelism focus. There's an excellent talk by Brian Getz, who's one of the senior architects of the Java platform, and he talks about the evolution of Java from concurrent to parallel computing. And so I recommend you watch that video. It's in the link at the bottom of the slide. And the point he makes there is that modern Java, namely Java 8 and beyond, combines functional programming with fine-grained data parallelism to more effectively leverage today's multi-core processors. And if you take a look at this diagram, which is from his talk, he makes the point that when cores were initially being introduced at larger and larger numbers, people thought that there would be this necessary uptick in performance. And it turned out that really wasn't what happened. The actual performance wasn't really keeping pace with the predicted performance to take advantage of all those cores. And so he describes how Java's support for data parallelism with things like parallel streams and completable futures is really designed to make it easier to take advantage of those cores. And I think that concept just goes on nicely in the more recent evolution to reactive streams and RxJava and Project Reactor. So really, we're taking much better advantage now of these cores than was the case in the past when we were using the earlier, more coarse-grained, concurrent, object-oriented frameworks like the Executor framework or the Executor completion service and so on. There's also another excellent talk by Rob Pike, who was worked at Bell Labs for many years. I believe he now works at Google. And he talks about some of the differences between concurrency and parallelism. And the point he makes, if you watch his video, which is also available at the link below, is that concurrency is about dealing with a lot of things at once, whereas parallelism is about doing a lot of things at once. So basically, that goes back to some things we've talked about earlier, where parallelism is really about running things at the same time on multiple processor cores, whereas concurrency is a bit more about coordinating interactions and synchronizing and passing information between different threads and sharing mutable data in a more effective and safe way. So that's the end of our overview of the history of parallelism support in Java.